Tonight, we're going to explore one of the most dangerous misconceptions in all of science. More than 15 billion miles from Earth, a small spacecraft built in the 1970s is quietly dying. Its name is Voyager 1, and it has traveled farther than any object human hands have ever made. Most people believe it has already left the solar system. It has not. It is not even close. When Voyager crossed the boundary the headlines called the edge of the sun's reach, it had completed roughly 0.1% of the true journey out. At its current speed, clearing the real edge would take close to 30,000 years. And it is still falling around a star it can barely see. By the end of tonight, you're going to understand why the true edge of the solar system lies not at the last planet but tens of thousands of years beyond it. How distance alone slowly starves a spacecraft of power, communication, and rescue. And what the dying Voyager probes reveal about the real danger of ever trying to leave. Before we get started, take a second to like and subscribe if you enjoy these videos. It really helps a lot. Now let's begin. 15 billion miles. Reading the number does not make it real, so slow down and sit inside it for a moment. Light itself, the fastest thing that exists, needs more than 23 hours to cross that gap in a single direction. Send a signal from that distance and it drifts through empty space for the better part of a full day before anyone on Earth hears it arrive. That is where Voyager 1 sits tonight, still transmitting, still falling slowly apart. Every year it loses about 4 watts of power, roughly the draw of a small nightlight, and that loss never reverses. It only adds up year after year, with nothing on the other end to top it back off. There is no plug to switch it to. There is no backup generator waiting in reserve. There is only the slow arithmetic of decline, running quietly in the background of a machine that is not allowed to stop working. Decades of that arithmetic already, and counting, with the losses never once running the other direction. What actually happens to a machine that far from anyone? Think about it plainly, without the movie music underneath. If a valve sticks, if a circuit shorts, if any one of 10,000 small components finally gives out after decades of cold and radiation, nothing changes on Earth's end. No rescue ship exists. No repair crew can be dispatched. No spare part is sitting in a warehouse anywhere along the way. Whatever breaks out there stays broken permanently, and the spacecraft either finds some way to work around the damage on its own, or it goes quiet. There is no third option. That is the condition Voyager already lives inside. Today, right now, while it is still transmitting. The true boundary is not the last planet, and it is not the place where headlines once declared the craft had broken free into interstellar space. It is the Oort cloud, a distant shell of icy debris that marks the actual edge of the sun's reach, and it sits nearly 2 light years out. Light itself would need close to 2 years to cross that distance. At Voyager's speed, actually clearing it would take something closer to 30,000 years. Longer than agriculture has existed, longer than cities, longer than writing itself. Longer, in fact, than the whole of recorded human history laid end to end. A machine assembled by hand in the 1970s would need to keep drifting, silently, through a region hostile and remote and utterly indifferent to human survival, for a stretch of time that dwarfs everything humanity has ever built or remembered. And by that true measure, the farthest object our species has ever launched has barely begun to move. Here's the picture almost everyone carries without ever really examining it. A spacecraft crosses some invisible line just past the last planet. The sun shrinks behind it to a bright, harmless dot. The stars ahead stretch out close and inviting, and the ship glides forward into whatever comes next. Weightless and unhurried, momentum doing all the remaining work. It feels natural. It feels like the obvious final step after everything that came before it. The way a story is supposed to end once the hero clears the last obstacle in the way. Almost none of it holds up. Not fairy tale wrong, where the broad shape is right and only the details are exaggerated for effect. Wrong the way a map is wrong when it was drawn by someone who never once left their house. Guess the proportions. Invent the distances. Sketch an emptiness on the page that bears almost no relationship to the emptiness it claims to represent. The comfortable picture was never built from measurement. It was borrowed from 100 other stories, from the shape of a satisfying ending, and quietly assumed to apply out here too, without anyone ever checking the numbers behind it. Nobody drew that map by walking the ground it claims to show. They drew it from memory of other maps, each one copied a little further from the original truth, and the danger people imagine follows that same borrowed shape. Picture the version from the movies. An explosion tearing through a hole in a shower of sparks. An alien presence stalking the corridors. A meteor storm hammering the windows while the crew braces and the orchestra swells behind them. Something loud and sudden that resolves itself, one way or another, inside a few tense minutes of running and shouting. That is not what actually waits out there. But here is the part worth sitting with. The part almost no one checks before believing the rest of the picture. Nothing about that fast, loud version matches what actually happens this far from home. It is worth saying plainly what does instead. Because the mismatch between the two pictures is the entire reason this danger goes so consistently underestimated. The real danger has no explosion anywhere in it. No alien, no impact, no single dramatic moment worth pointing a camera at. It is slower than that. It is quieter than that. It is the steady, compounding collapse of every system and every assumption that made the journey feel survivable in the first place. Power that fades a little further with each passing year. Signals that grow fainter with every added mile. Support that thins out gradually until, one day, without any single alarm ever going off, there is nothing left to lean on. Nothing breaks all at once out there. Nothing announces itself. There is no single moment to point to, no alarm, no countdown clock. Everything breaks slowly, together, at its own pace, quietly enough that the collapse is already well underway, long before anyone thinks to notice it has started. So what does it actually mean to leave the solar system? Ask almost anyone, and the answer arrives without a moment's hesitation. Pass the last planet. Cross some boundary. You are out. Simple as that. Done in a single breath. No further thought required. That instant confidence, arriving before any real reasoning sits behind it, is itself the clue worth following. It means the picture was never actually examined, only inherited, passed down from one telling to the next, until repetition alone hardened it into something that felt like fact. It deserves a far closer look than anyone tends to give it. And the real distances involved are stranger and considerably larger than the borrowed picture ever let on. Start with the boundary itself, the one the headlines already got wrong once. Neptune looks like a reasonable place to stop. 8 planets run from Mercury out to Neptune, and Neptune is the last one anyone officially counts. It orbits roughly 30 astronomical units from the Sun, and 1 astronomical unit is simply the distance from Earth to the Sun, about 93 million miles. Picture that single distance as 1 step. Neptune then sits 30 steps out. Multiply the miles instead, and Neptune comes to close to 2.8 billion miles from home. Light needs more than 4 hours to cross that gap. A spacecraft moving at Voyager's speed, about 38,000 miles an hour, would still need over 12 years just to reach where Neptune orbits. That already sounds enormous. 30 steps into a walk that, it turns out, has barely begun. Measured against everything still ahead, Neptune is embarrassingly close. Push past Neptune and the debris begins. The Kuiper Belt is a wide ring of icy bodies and dwarf planets, stretching from about 30 to 50 steps out, 30 to 50 astronomical units, holding far more material than most people picture when they picture it. Pluto lives here. So do Eris, Makemuk, and Haumea, along with thousands of smaller frozen objects drifting through the same dark ring, each one its own small, cold world. Ask most people where the solar system actually ends, and this is the region they picture. Somewhere around 50 or 60 steps out. The last named world, and whatever surrounds it. Not even close. Farther out, the sun still has one more trick. It exhales constantly, a stream of charged particles called the solar wind, moving anywhere from 700,000 to nearly 2 million miles an hour. That wind pushes outward against the thin gas and dust, drifting between the stars, and the pushing inflates a vast bubble around the entire solar system. That bubble is the heliosphere, the sun's true reach through direct material contact, not starlight, not gravity, just the wind itself holding the galaxy back. Depending on direction and the sun's own activity, the bubble stretches somewhere between 90 and 120 steps out before the push finally runs dry. The edge of that bubble carries its own name, the heliopause, the place where the solar wind finally loses its long fight against the pressure of interstellar space, where the sun stops shoving and the galaxy starts to win. 90 to 120 steps out. Still nowhere close to 100,000. On August 25th, 2012, Voyager 1 crossed that line at about 122 astronomical units out, 122 steps into the walk. Voyager 2 followed on November 5th, 2018, a little closer in at 119. Headlines everywhere announced that humanity had finally reached interstellar space. Technically, that was true. Past the heliopause, the plasma, the magnetic fields, and the particles drifting through the dark all belong to the galaxy now, not the sun. It felt, to almost everyone watching, like the finish line. For years afterward, that crossing was treated as the answer to the question this whole walk keeps circling back to. Where does the solar system actually end? As far as the public conversation was concerned, the question was closed. Wait, reaching interstellar space is not the same as leaving the solar system. The sun's wind runs out of strength at 120 steps from home. Its gravity does not. Wind is a shove, strong up close and spent within a couple hundred steps. Gravity is a leash, thinner and thinner the farther it stretches, but never quite letting go. It fades with distance without ever actually reaching zero, and the sun uses that quiet, patient pull to hold objects in orbit at distances that make the heliosphere look like a puddle. A boundary defined by wind will always be smaller than one defined by gravity, because wind runs out of energy and gravity, as far as anyone has measured, simply does not. The heliopause was never the edge of the sun's territory. It was only the edge of its breath, not a boundary, barely a doorstep. Out past that doorstep sits the Oort cloud, a shell of icy bodies that may begin around 2,000 steps out, and keep going to 100,000, possibly further. Some estimates push the outer edge to 200,000 steps. Nobody has ever seen it directly. It is inferred, not observed, and the honest answer is that its true edge, its density, its very shape remain genuinely unknown. That uncertainty is not a gap in the story. It is the story. Even the people who study this for a living are still walking blind past a certain point. And that same uncertainty spreads into everything that depends on it. If no one agrees where the cloud actually ends, no one can say with confidence how long it would take anything to cross it either. For a sense of just how far that unknown edge might be, 1 light year works out to about 63,000 astronomical units. 63,000 steps in this walk. The nearest star beyond our own sun, Proxima Centauri, sits 4.25 light years away, close to 268,000 steps from where we started. The outer edge of the Oort cloud may reach more than a third of the way there. Hold those two numbers together for a moment. 63,000 steps for 1 light year. 268,000 steps to the nearest star. The Oort cloud does not just border our solar system. By some estimates, it very nearly borders theirs. The space between our sun and the next one over is not empty the moment the planets fall behind. Long before Proxima ever comes into view, all of it, every last step of it, still belongs to us. Here is the number worth sitting with. Voyager 1, at the heliopause, the crossing that made every headline on Earth, had walked 122 of these steps. The Oort cloud's outer edge sits at 100,000 steps, at least. Set the two side by side. 122 out of 100,000. Walk it out. 122 steps taken. 99,878 left, standing between here and the edge, and that is measuring to the nearest edge anyone has proposed. Round the fraction down, and what is left is not 1% of the journey. It is 1/10 of 1%. Say it again, slowly, because it does not get any less strange the second time. 1/10 of 1%. After decades of travel, at full speed, the entire time. Keep that speed running for decades more, and the spacecraft still needs tens of thousands of years to clear what remains of the cloud. Every one of those years, it stays caught in the sun's pull, still orbiting, still technically home, circling a star that by then would be too faint to even see from out there. Leaving the solar system was never going to be a single crossing of a line. It is a process so long, so gradual, that no one alive today, measured any way you like, would live to see it finished. Not because the fuel would run dry, not because of any single dramatic failure, simply because the distance itself is that large, and distance out here does not negotiate. And that boundary at the heliopause, the one that made the headlines, the one everyone assumed meant departure, turned out to be doing something else entirely. Something that had nothing to do with distance at all, and everything to do with what it had quietly been holding back. Something no one thinks to ask about until it is already gone. Ask what the heliopause had been quietly holding back, and the answer is not scenery. It is not a line drawn for the convenience of map makers. The heliosphere, that whole bubble the solar wind blows outward around the sun, turns out to be a shield. It has been standing between the solar system and something considerably worse than empty space for as long as the sun has been blowing that wind, and almost no one thinks about it until the moment it stops. Out in the wider galaxy, stars die badly. Supernovae detonate. Neutron stars spiral into each other and collide. Ordinary stars, just going about their business, throw off bursts of violence in the normal course of living and dying. Strip away the specifics and the result is the same every time. Streams of protons and heavier atomic nuclei get hurled outward at speeds close to the speed of light. These are galactic cosmic rays, and calling them fast barely covers it. They carry enough energy to punch straight through a spacecraft's hull. They can flip a single stored digit inside a computer's memory without leaving a mark on the case. And over years, they leave paint discolored, insulation brittle, and metal itself subtly weakened from the inside. Pass one through a strand of DNA, and it can break the strand outright, once, then again, then in a different place the next time. None of that requires a collision, an explosion, or a single dramatic instant. It only requires time, And out past the heliopause, time is the one thing there is no shortage of. What keeps that violence from reaching the inner solar system in the first place is not a wall. It is closer to a net, woven out of the sun's own spinning magnetic field and dragged outward by the wind, twisting into a loose spiral as the sun turns. Incoming particles do not simply bounce off it. They get bent, deflected, forced onto longer and more tangled paths, so that many of them lose the fight before ever reaching the planets. It is not a perfect net. Some threads are looser than others depending on how active the sun happens to be that year. But loose or tight, it is still doing more work every single day than almost anyone standing under it ever stops to consider. Inside the heliosphere, most of that violence never reaches you. The sun's own magnetic field, carried outward on the solar wind, bends and scatters a large share of incoming cosmic rays before they ever reach the inner solar system. Not all of them. Some still slip through, which is why cosmic rays do reach Earth even now. Filtered, but never fully stopped. Reduced is the honest word for what the sun does out here. Not eliminated. Reduced. By a margin large enough to matter, every single day, to everyone standing on this planet without ever noticing the favor being done for them. But here's where it gets stranger. Nobody had to guess how large that margin actually was. Voyager 1 measured it directly, in real time, the moment it crossed the heliopause. Its instruments, still counting particles after decades in flight, recorded a sudden climb in galactic cosmic ray intensity. Not a gradual drift upward. A step. The counters jumped, and they jumped by almost exactly the amount the models had already predicted, as if the universe had confirmed its own homework in front of everyone watching. Outside the bubble, the radiation environment is not slightly harsher. It is measurably, sharply harsher, and Voyager's own instruments are the proof, sitting in a data archive on Earth, for anyone who wants to check the math. That confirmation is part of why NASA built something new. The Interstellar Mapping and Acceleration Probe, IMAP for short, launched in September 2025 and reached its post at the Sun-Earth Lagrange point 1 that January. A stable patch of space where the pull of the Sun and the pull of Earth balance closely enough that a spacecraft can sit there without burning fuel to hold its ground. From that vantage point, IMAP exists to map the heliosphere's boundary in a level of detail no earlier mission could manage, watching how its shape and thickness shift over time and from one direction to another. Its instruments are roughly 30 times more sensitive than the ones on its predecessor. A smaller mission called the Interstellar Boundary Explorer, picture trading a pair of household binoculars for a research telescope aimed at the same patch of sky. Same target, 30 times the detail. That leap in sensitivity is not academic curiosity. The shape, thickness, and variability of this boundary determine how much galactic radiation reaches the inner solar system today, and how much more of it any future spacecraft would face the moment it left. And a spacecraft is the easy case. Any mission that someday carries people rather than instruments would be committing years of a human life to whatever lies on the far side of that map, which is exactly why getting the map right before anyone commits to the trip matters as much as it does. Here is the point worth sitting with. The sun is not only handing out light and warmth, it is actively defending everything inside its reach from a harsher galactic environment, every hour of every day, without being asked and without sending a bill. So what happens the moment that defense is gone? Not a slow dimming you might adjust to over years, the way sunlight itself fades with distance. A threshold, crossed once at the heliopause, the same step Voyager's counters recorded, and never cross back. Past that threshold, the exposure is total. There is no reduced version of galactic cosmic rays waiting on the other side, only the unfiltered stream arriving from every direction the sky offers, all at once, all the time. And this particular danger does not announce itself. It carries no alarm, no countdown, no single dramatic moment to mark its arrival. It behaves more like rain filling an open container left out in a storm. No single drop matters. Nobody hears a splash. It simply accumulates, particle by particle, hour by hour, year by year, in holes, in circuitry, in anything alive, and it does not pause to let anyone catch up. Even now, the fine print stays open. Exactly how thick the heliosphere is, how its shape shifts with the sun's own moods, how much that shape varies from one direction to another, all of that is still being mapped, which is the entire reason IMAP exists in the first place. Nobody yet has a precise number for how much worse the exposure gets 100 steps past the boundary, or 1,000. The honest answer is that the instruments tracing the shield's edge are only beginning to sketch its true outline. What is not uncertain is which spacecraft is already living on the far side of it. The same instruments that caught that sudden jump in cosmic rays belong to a machine that has spent every day since bathed in the exposure the rest of us have only read about. And that machine is not getting any younger. That machine is Voyager 1, and its twin, Voyager 2, is aging right alongside it. Both launched in 1977. Both were built for a 5-year mission, a modest goal by any measure. Both are still transmitting today, closing in on 48 years of continuous operation, decades past anything their own engineers expected to still be reading data from. Call it a miracle of engineering if you want. It is also a bill that has been coming due quietly every year since launch, and the balance is running out. These two machines are the only objects humanity has ever placed beyond the heliosphere. No other spacecraft has followed them out. That makes their story more than a footnote about two aging probes. It is close to the entire dataset on what deep space actually does to a machine, given enough time, and the answer it hands back is patient, unglamorous, and impossible to argue with. Neither spacecraft carries solar panels. This far from the sun, a panel would be dead weight, staring at a light source too faint to matter. Instead, each Voyager runs on a radioisotope thermoelectric generator, a sealed canister of decaying plutonium-238, whose heat gets converted directly into electricity. No moving parts, no fuel line, no way to add more fuel once the canister is closed. At launch, each generator produced about 470 watts. As of 2026, that number has fallen to roughly 220, less than the power it takes to run a single household light bulb. Two spacecraft that once ran a dozen instruments, a working radio, onboard heaters, and a data recorder now share, between the pair of them, less electricity than one lamp on a nightstand. The consequence has arrived instrument by instrument. In February 2025, engineers on the ground shut down Voyager 1's cosmic ray subsystem, a piece of hardware that had been counting particles since before most of the people running it today were born. The next month, they did the same to Voyager 2's low-energy charged particle instrument. Only 3 science instruments remain active on each probe. More shutdowns are already scheduled for 2026. The mission team hopes to keep at least one instrument breathing on each spacecraft into the early 2030s, and they have said plainly, without hedging, that an unforeseen failure could end either mission at any moment, with no warning and no countdown. Each shutdown is permanent. There is no powering an instrument back on once its share of the wattage has been handed to something else. Notice what is missing from that list. No collision, no explosion, no hostile encounter with anything out there in the dark. The farthest machines humanity has ever built are not being destroyed. They are being starved. Plutonium decays at its own fixed rate, indifferent to mission schedules, indifferent to how badly anyone on Earth wants more time. Not a dramatic ending. A slow one, done entirely in arithmetic. There is no way to refuel a spacecraft 15 billion miles from the nearest source of power. There is no way to swap a generator, no way to send a technician, no way to do anything at all except watch the wattage fall and plan around it. Deep space does not kill quickly. It waits, and it lets the batteries run down on their own schedule, not yours. Power is only half of what is fading. Voyager 1's radio transmitter puts out about 23 watts, less than the bulb inside a refrigerator. That whisper of a signal has to cross the same 15 billion miles, spreading thinner with every mile, the way ripples thin as they widen across still water, until by the time it reaches Earth, it takes the largest receivers NASA owns just to hear it at all. Those receivers are deep space network dishes 70 meters across, roughly the height of a 20-story building laid on its side and pointed at the sky. Even with that much steel listening, the data comes home as a trickle. The spacecraft that once sent back crisp photographs of Jupiter's storms and the rings of Saturn now sends columns of numbers, slowly. A single new photograph, if there was still a working camera worth pointing, would take weeks just to arrive. What used to be a torrent of images has narrowed, year after year, into something closer to a pulse, faint but still counted, still logged, still proof that something out there is alive. And the delay keeps stretching. A signal from Voyager 1 still needs more than 23 hours to make the crossing. By November 2026, the spacecraft will pass one light day from Earth, the point where a message sent and answered takes a full 48 hours to complete the round trip. Wait. 2 full days, and Voyager has not even reached the Oort cloud yet. If something breaks inside that window, there is no fixing it from a console on Earth. The onboard computer, technology from the 1970s, has to recognize the fault and protect itself alone, because by the time a warning arrives and a fix is sent back, the moment it could have helped will already be gone. Here is the part worth sitting with. Voyager 1 is currently about 173 astronomical units from the Sun, further than any other human object has ever traveled, and still nowhere close to done. It has not reached the Oort cloud. It has not come close to leaving the solar system by any definition that actually holds up under scrutiny. And already, at this distance, the mission is being flown at the outer edge of what is survivable. Fading power, a whisper for a voice, instruments going dark one at a time, a control room on Earth that arrives a day late to every decision that matters. This is not a spacecraft in trouble because something went wrong. This is a spacecraft behaving exactly as physics predicted it would, 48 years into a 5-year plan, simply running out of road. Push that same math further out, toward the Oort cloud and beyond. At 10,000 astronomical units, a message crawling at the speed of light needs about 2 months just to arrive. At 100,000 astronomical units, roughly where the Oort cloud thins into true interstellar space, the one-way trip stretches past a year and a half. Send a question at that range and wait for the answer, and the round trip eats more than 3 years. 3 years, spent entirely on saying hello and hearing it land. A fault that would take an engineer on Earth an afternoon to diagnose becomes, at that range, a problem the spacecraft has to solve entirely alone, with whatever logic was written into it years or decades earlier by people who could not possibly anticipate every failure a strange new environment might cause. Past a certain distance, mission control stops being control at all, not guidance, not correction, silence, and a machine that has to decide things for itself. It becomes a message sent into the dark, addressed to a spacecraft that might already have gone quiet by the time the message arrives, with no support, no course correction, and no one on Earth able to do a single thing about it either way. 2 aging probes, built with 1970s technology, are already living out the first chapter of that story. A chapter that started the moment they crossed the heliopause and has been playing out in slow motion ever since. Power was the first system to go. It would not be the last, but calling it first only matters if there is a second and a third, and the reason there is a list at all traces back to one source, one star, quietly doing more work than anyone standing in its light ever stops to notice. The sun does not spend its energy evenly. It follows a rule called the inverse square law, and the rule is almost insultingly simple. Double the distance from the source, and the energy landing on any given patch of space drops to a quarter. Triple it, and the energy drops to a ninth. Near Earth, the sun delivers about 1,360 watts to every square meter it touches, more energy packed into that single square meter than a microwave oven pulls from a wall socket. Out at Jupiter, 5 times farther from the sun than Earth is, that number collapses to around 50 watts per square meter, enough to run a couple of household lamps and little else. At Neptune, 30 times farther than Earth, it thins to roughly 1.5 watts per square meter, about what a small candle throws off, not enough to warm the back of your hand. And at the heliopause, the boundary this story has already crossed once. Sunlight has faded so far that even the largest solar panels ever engineered could not power a household toaster. Past that point, the sun stops being useful as a power source in any practical sense. It still burns. It is still there, a bright point holding its place among the stars. But it can no longer do the one job every spacecraft has quietly depended on since the day it launched. So anything traveling beyond the heliopause has to carry its own energy with it, sealed inside a canister of slowly decaying plutonium, ticking down from the moment it was manufactured, with no way to add fuel and no way to slow the decay once it begins. There is no refueling station out there, no depot, no passing ship willing to lend a hand. Whatever energy a mission launches with is the only energy it will ever have. For a mission measured in decades, that clock is survivable. Engineers can plan around it, budget for it, schedule instrument shutdowns years ahead of time, the way the last stretch of this story already showed happening in real time. But stretch the mission to centuries, or to the millennia the Oort cloud actually demands at any speed humanity can currently build. And that same clock becomes something else entirely. Power runs out, instruments go dark, heaters fail, electronics freeze solid in the cold between the stars, and the spacecraft, once humanity's farthest reaching machine, becomes indistinguishable from the debris it passes. But here's the part that reframes everything that came before it. The picture most people carry of leaving the solar system treats it like leaving a harbor. Untie the ropes, raise the sails, head out into open water. A ship built well enough runs the same 1 mile from shore as it does 1,000 miles out, because the ship was never depending on the harbor to keep functioning. It only needed the harbor to launch from. Not this. A spacecraft is not a ship on open water. It is closer to a diver still breathing through a hose that runs all the way back to the boat. The harbor, in this case the sun and the earth together, is not just the place a mission departs from. It is the reason everything works at all. The sun supplies the energy. Earth supplies the communication link, the navigation corrections, the repair capability, the emergency support, and the quieter thing underneath all of it. The simple fact of someone back home listening. None of that is glamorous. None of it makes headlines the way a launch does. It is infrastructure, the kind that only gets noticed once it starts to fail. Every mile of distance costs a fraction of each of those systems. Power thins, signal thins, correction thins, support thins, and at some point far enough out, the losses stop being fractional and start being total. That point is not a wall. There is no sign, no line drawn on any map, no single moment where an alarm sounds and everything stops at once. It is a gradient, a curve bending downwards so gently that day to day, nothing seems to change. A mission could cross it without anyone on the ground being able to point to the exact hour it happened. Step back far enough to see the whole shape of the curve though, and it is unmistakable. Power, communication, support, rescue, recovery, all of it, sliding along the same slow arc towards zero, at different speeds, but toward the same destination. And the distance where that curve finally flattens out completely is not the distance to Mars. It is not the distance to Pluto. It is not even the distance to the heliopause, already crossed by 2 aging probes decades ago. It is the distance to the true edge of the sun's reach, a region so vast that light itself needs longer than a year just to cross it. The same edge this story has already measured once, in numbers too large to hold on to. So here is the definition this whole piece has been circling since the opening minutes. Leaving the solar system does not mean a dramatic crossing, a line stepped over, a boundary passed in an instant. It means a slow, irreversible descent into a condition where every system emission depends on weakens, where every connection to safety thins, where every option for rescue and recovery quietly disappears. Not because of one catastrophic failure, not because of any single event at all, because of the single most fundamental force in the universe, distance. That is only half of what is waiting out there, and it is the gentler half. Losing the sun's energy and losing Earth's support explains why a spacecraft slowly starves. It does not explain what that spacecraft is starving inside of. A dying power supply is a problem of arithmetic, decay curves, and watts and years. Cold, but at least predictable. What lies past the heliosphere is not predictable in the same way. Beyond it sits an environment that does not simply fail to help. It actively works against anything that crosses into it. And the deeper that crossing goes, the more hostile it becomes. That hostility is still ahead. What has already been happening, quietly, for decades, sits much closer to home. Every machine that has ever operated beyond Earth survives inside something larger than itself, an invisible web of systems built to keep it alive, and none of that web travels through space, bolted to the hull. Communication links carrying commands out and data back, navigation corrections sent from the ground, recalculated and uploaded whenever the craft drifts off its plotted course. Power sources sized, in theory, for the length of the mission. Thermal management to keep instruments from freezing in shadow or cooking in raw sunlight. Contingency procedures rehearsed for years by engineers who can, for now, respond within minutes or hours when something goes wrong, running simulations of failures that have not happened yet, so the real ones are less of a surprise. None of that web is the spacecraft itself. All of it is why the spacecraft works at all. That web has a range. It was never built to reach forever, and it does not. Every strand weakens with distance, but not evenly, not together. Communication follows one physical law, power follows another, navigation follows a third. Each one crosses its own failure threshold at its own distance from the sun, on its own schedule, for its own reasons. So what actually happens at the edge of that web? Not a switch flipping off. Not a single wall where the whole system stops at once. There is a cascade, one support sliding below the line that keeps a mission alive, then another, each collapse setting the terms for the ones still to come. The unsettling part is not that it happens, it is how early it starts. Sometimes before a mission has travelled a fraction of the distance anyone assumed it had room for. power goes first. Without electricity, nothing else in the story functions at all. Instruments go blind, computers stop thinking, heaters shut off, antennas fall silent, unable even to transmit a whisper. Valves freeze in whatever position they last held. A spacecraft with no power is not a broken machine. It is a rock, tumbling on a very expensive, very deliberate trajectory. For a while, sunlight itself is enough. Modern solar panels can still pull meaningful power as far out as Jupiter, roughly 5 times Earth's distance from the Sun. NASA's Juno spacecraft has proven it, orbiting Jupiter since 2016 on nothing but sunlight. Its 3 panel arrays spanning more than 66 feet, tip to tip, about the length of 2 school buses parked end to end. At Jupiter, the Sun delivers only around 4% of the energy it gives Earth. Juno's arrays still manage to squeeze out roughly 500 watts from that thin trickle of light. It works. It works barely. Push past Jupiter and sunlight stops being useful at all. At Saturn, roughly 10 times Earth's distance, the Sun provides only about 1% of what it gives Earth. At Uranus, 20 times out, less than a quarter of 1%. At Neptune, 30 times out. The number is close enough to nothing to call it nothing. No solar panel that exists today, or that anyone expects to build within decades, can pull usable power from sunlight that faint. The Sun is still burning out there. It is still visible, a steady point of light in every image these spacecraft send home. It has simply stopped being useful, still shining, and functionally dead as a power source. So everything travelling past Jupiter runs on something else entirely, the same technology carrying Voyager through the dark right now. A radioisotope generator works on a simple principle. Plutonium-238 decays, and decay releases heat, the way a coal ember keeps giving off warmth long after the flame is gone. 2 different metals joined together convert that heat difference into a small, steady electrical current. No moving parts to wear out, no combustion, no valves, no fuel used up in a single burst. Just the slow, patient release of energy from atoms quietly falling apart, hour after hour, for as long as any of it remains. Here's the cruelty built into that patience. Plutonium-238 has a half-life of roughly 87.5 years, nearly the span of a long human life. Every 87.5 years, half of whatever plutonium remains has decayed into elements that produce less usable heat than before. Power output does not fall in sudden drops. It slides down a smooth, relentless curve. A Voyager-class generator losing about 4 watts every year, the same quiet decline already measured earlier in this story. Nothing stops that curve, nothing slows it, nothing reverses it. The countdown starts the moment the plutonium is sealed inside the generator, and it never pauses again. For a mission measured in years, that decline is survivable, even predictable. New Horizons carried a generator like this past Pluto in 2015, its output starting near 240 watts at launch, roughly enough to run a couple of bright reading lamps, and settling to about 208 watts by the time it reached Pluto 9.5 years later. A real loss, measurable and accounted for, not a crisis. Engineers had modeled that exact curve years in advance, built the whole mission around it, and knew almost to the watt what the spacecraft would have left when it finally reached its target. Stretch that same mission from years into centuries, and the curve stops being manageable. A trip to the heliopause takes decades. A trip through the Oort cloud, at any speed humanity can currently build, takes centuries, sometimes millennia. After 3 half-lives, something like 263 years, the plutonium retains only about 12% of its original heat. After 5 half-lives, close to 438 years, barely 3% remains. Not enough to run one instrument, not enough to hold back the cold. The generator goes quiet. The electronics freeze solid. A machine that once represented the outer edge of human engineering becomes silent metal, drifting, indistinguishable from the debris around it. And there is no alternative waiting in reserve. Fusion power, if anyone ever manages to build a version small enough and light enough for a spacecraft, might one day change this math entirely. A reactor that does not run down the way a lump of decaying plutonium does. As of 2026, no working fusion reactor has ever flown, not for power, not for propulsion, not in any spacecraft built by any nation. It remains a hope on paper, not a system anyone can launch. Beamed power, the idea behind Breakthrough Starshot, only helps for a moment. A laser or a microwave station near the sun, pushing a tiny feather-light probe up to speed during its first minutes of flight. Once that probe drifts beyond the beam's reach, the boost ends, and it is on its own, as alone as everything else out there. It would be comforting to think this is a design problem, something a smarter engineer could eventually solve. It is not. Radioactive decay does not negotiate. There is no material, no clever circuit, no backup plan that changes how fast plutonium falls apart. Past a certain distance, physics alone makes sustained power impossible. Not unlikely, not difficult, impossible. For any machine humans currently know how to build. Power was the quietest of the 5 failures still ahead, asking for nothing, announcing itself to no one, simply thinning until there was nothing left to draw on. 4 more waited in the dark. The next one would surface the moment anyone on Earth tried to say something back. Even a spacecraft with power still humming inside it is only as alive as its ability to be heard. That is the second collapse in the web, and unlike power, it does not fail quietly on its own schedule. It fails on 2 fronts at once. The first front is time. Radio waves travel at the speed of light, about 186,000 miles every second. Nothing in the universe moves faster, and no engineer will ever build something that does. That ceiling is not a technical limitation waiting on a better antenna or a smarter chip. It is a wall built into the universe itself. And yet, against these distances, that speed is grotesquely slow. At Mars, a signal takes 3 to 22 minutes each way, already too sluggish for real-time control. Every command decided minutes ago, every response minutes late by the time it lands. At Jupiter, the one-way wait stretches toward an hour. At the heliopause, it reaches 17 hours. Voyager 1 signal, right now, needs more than 23 hours just to arrive. And every one of those numbers only grows. By November 2026, Voyager 1 will sit a full light day from Earth. The milestone this story has already marked. Picture what that means in ordinary time. An anomaly appears Monday morning. Earth does not learn about it until Tuesday. The corrective command reaches the spacecraft Wednesday. Confirmation that it worked comes back Thursday. 4 days to close one loop for a craft that is still, by the standards of what lies ahead, right next door. Push the same math out to the Oort cloud, and days become weeks, then years. At its inner edge, roughly 2,000 astronomical units out. A message needs about 11.5 days to arrive. 23 days for a full round trip. The better part of a month spent waiting on a single answer. At the outer edge, the wait stretches into the same 1.5 years. 3-year round trip. This story has already sized up once before. Ask a question from there, and you may not hear the answer until you are 3 years older. But delay was not the worst of it. The second front, signal strength, was crueler. Radio signals do not travel as a tight beam. They spread, the way ripples widen and thin across still water. carrying the same total energy across an ever larger circle. Power falls with the square of the distance. Work it slowly. Double the distance and the signal does not fall by half. It falls to a quarter. Triple the distance and only a ninth survives. Push the distance out tenfold and just 1/100th remains. The farther the whisper travels, the faster it fades. And it fades faster than distance alone would suggest. Voyager transmits on the same 23-watt signal this story has already named. After more than 15 billion miles, that signal has spread so thin that by the time it reaches the network's largest dishes, the power arriving measures close to 10 to the minus 16 watts. A decimal point, 15 zeros, and then a 1. Detecting something that faint requires cooling the receiving equipment to nearly absolute zero, just to quiet the electronic noise enough to hear it, and even then the whisper needs layers of amplification and error correction before it means anything at all. This is at only 173 astronomical units. The Oort cloud has not even started. What survives the trip carries almost nothing. Voyager 1's data rate has dropped to about 160 bits a second, something like 1/16,000th the speed of an ordinary home internet connection. A single photograph at that rate would take weeks to arrive. Not slow, barely a trickle. Scale the distance up and the trickle disappears entirely. 10 times farther out, the signal is 100 times weaker. 100 times farther, 10,000 times weaker. Somewhere near the outer edge of the Oort cloud, a Voyager-class transmitter signal would be too faint for any antenna on Earth, including ones nobody has built yet, to detect. The craft would keep transmitting. The waves would keep spreading outward at light speed, exactly as they always have. But the whisper would fall below the floor of what anything on this planet could hear. Even inside the distances where a signal can still be caught, the ability to listen rests on something smaller and more fragile than most people imagine. The Deep Space Network is the only system on Earth that can talk to anything past the moon. And it runs on 3 big dishes spaced about 120 degrees apart near Canberra, Madrid, and Goldstone, so that as the planet turns, one of them always has a clear line of sight to the sky. It does not exist for the Voyagers alone. Mars rovers use it. Solar probes use it. IMAP, the newest mission mapping the shield this story described earlier, uses it too. Missions from the European and Japanese space agencies use it. Every one of them competes for the same handful of dishes, and only a few of those dishes are large enough to hear anything at extreme range. Antenna time is rationed hour by hour, allocated by urgency, and for 2 decades demand has outpaced what the network can actually give. A system built to listen for a handful of missions now listens for dozens, on the same 3 dishes it has always had. In May 2025, that fragility stopped being an abstraction. Deep Space Station 43, the 70-meter dish at Canberra, is the only antenna in the entire network large enough to send commands to either Voyager. Not one of the other big dishes could substitute, only that one. It went offline for major upgrades, and did not fully return until February 2026, with only narrow windows in August and December when engineers could reach the spacecraft at all. Outside those windows, a serious fault on either probe would have gone uncorrected, and there would have been nothing anyone on Earth could do about it. Survival, for months at a stretch, depended entirely on 2 nearly 50-year-old machines catching their own mistakes and quietly fixing what they could, with no one watching and no one able to help. Push the projection further and the picture does not improve. A craft at 1,000 astronomical units would need receiving sensitivity far beyond anything the current network can offer. At 10,000 astronomical units, the requirement moves into territory that would demand a fundamentally different kind of radio telescope, one large enough and sensitive enough that nothing like it has ever been proposed in earnest, let alone funded, planned, or sketched on paper. No agency on Earth is working on it. No agency has said it should. So the conclusion is not that communication with something at the edge of the solar system gets slow, the way traffic gets slow, or a connection gets slow on a bad day. It is that communication with something at the edge of the solar system stops. Not thinner, not weaker, gone. The link severed by physics on one side, and by the limits of what humans have built to listen on the other. Power failed in silence, a curve sliding towards zero with nobody watching. This second collapse is louder, measured out in years of waiting and whispers too faint to catch. And the moment a spacecraft can no longer be heard, in every sense that matters, it also becomes impossible to find. Impossible to find is not a separate misfortune that happens to arrive after the signal dies. It rides in on the same failure because knowing where a spacecraft is turns out to depend on hearing from it. That is the third collapse, navigation, and it doesn't wait politely for the communication to finish falling apart first. It falls with it, quietly, the way a shadow falls the instant the light it depends on goes out. Deep space offers nothing to navigate by in the way Earth does. No landmarks, no roads, no constellation of satellites overhead to triangulate against, the way a phone in your pocket does without you ever thinking about it. Out past the planets, there is no ground to measure from, no fixed shoreline, nothing solid except the stars themselves, and the stars alone cannot tell a spacecraft how far it has travelled. They can only tell it which way it happens to be facing. Direction without distance is not navigation. It is only a heading, and a heading tells you nothing about how far along that heading you actually are. So every deep space mission NASA has ever flown has located itself the same patient way, through radiometric tracking. A ground station sends a precisely timed signal outward. The spacecraft catches it and sends it straight back, like a voice bouncing off a canyon wall and returning to the person who called it. Engineers time that round trip down to fractions of a second and measure how the frequency shifted along the way. A Doppler shift, the same stretch and squeeze that changes an ambulance siren's pitch as it passes. From timing and shift alone, they calculate distance and velocity with extraordinary precision, precise enough to guide a spacecraft through a planetary flyby thousands of miles wide from billions of miles away. It is an elegant trick. It has guided every probe humanity has ever sent outward, from the earliest missions to the edge of the heliosphere and beyond. And it depends completely on the exact same fragile thread that carries every command and every whisper of data home. There is no separate channel for position. The location of a spacecraft and the sound of its voice travel down the identical wire. This is where the third collapse and the second one stop being two different stories. If a signal is too faint to detect, there is nothing to time and nothing to measure, and radiometric tracking simply fails. If the delay stretches long enough, the numbers that do arrive describe where the craft used to be, not where it is now. A position reading from an hour away is current. A position reading from a year away is a year old. A snapshot of a place the spacecraft left long before the number ever reached Earth. Ask where it is right now, and the honest answer is that no one can say, only where it was. Onboard instruments cannot close that gap. Star trackers, small cameras that compare the pattern of stars overhead against a stored map of the sky, can tell a spacecraft which way it is pointing. Orientation only, not position. A ship can know its bow points north and still have no idea how many miles of ocean it has crossed to get there. No system exists, on any spacecraft ever built, that can determine its own location at interstellar range without help from Earth. Not roughly, not approximately, not at all. The instrument that could do that has never been designed, because until now, nothing has needed to travel far enough to require one. That leaves the same overstretched network already carrying every command to the Voyagers, now carrying the weight of finding them too. The Deep Space Network is a marvel built for a solar system, not for the distances waiting past it. And even its largest dishes have hard physical limits. A floor beneath which a signal cannot be caught, and a ceiling on how far anything can be tracked with useful precision. The single dish, already established as the only one able to command either Voyager, is the same single dish responsible for knowing where they are. One antenna, doing both jobs at the ragged outer limit of what either job can do. What happens to a mission's sense of place when its only compass and its only phone line are the same fragile piece of hardware, thousands of miles from any backup? Nothing good, and nothing that can be fixed by building a second dish somewhere else, because the limit is not the number of antennas. The limit is how faint a whisper any antenna, anywhere, can still hear. The pattern by now is familiar, and worth naming plainly. Power failed in silence, a curve sliding towards zero with nobody watching. Communication failed loudly, years of waiting stretched thin over a whisper too faint to catch. Navigation fails as neither. It fails as an after-image, a shadow with no light left to cast it. A spacecraft that cannot be heard cannot be tracked. A spacecraft that cannot be tracked cannot be found. And a spacecraft that cannot be found, however carefully built, however precisely aimed at launch decades earlier, drifts blind through the dark, its last known position aging by the day into something closer to fiction than fact. Navigation in deep space works. That much is true today, and has been true for nearly 5 decades of NASA missions guided the same patient way. It works right up until the link it borrows from gives out, and then it does not degrade gracefully. It stops all at once, with nothing on board able to pick up the slack. This was the third of the 5 collapses, the leanest of them, built on a single dependency rather than a tangle of failing parts, and no less final for its simplicity. 2 more still waited in the dark. The next one did not ask whether a spacecraft could be heard or found. It asked what happens the day something on board simply breaks, with no one able to reach it either way. Suppose the answer is yes. Suppose something on board simply breaks, a valve sticks, a circuit shorts, a fuel line freezes solid overnight. The question was never whether it would happen eventually. Complex machines fail, given enough time, that much is close to a law of nature. The real question is who comes to fix it. In low Earth orbit, roughly 250 miles up, about a drive you could finish before dinner if you left in the morning, repair is hard but far from impossible. Astronauts suit up, cycle through an airlock, and step outside the station to fix what needs fixing. Tethered, patient, working through a checklist rehearsed on the ground months in advance. Resupply ships arrive on a rotating schedule. Cargo capsules loaded with exactly the parts engineers already know will eventually fail. A replacement part can launch within weeks, sometimes days. Help, in the language of deep space, is close. Farther out, at the moon, nearly 240,000 miles away, the math gets harder. Drive that distance at highway speed without ever stopping, and the trip takes close to 5 months of non-stop driving, day and night, no stops for gas or sleep. Response times stretch. Resupply costs more and has to be planned further in advance, but it is still physically achievable. And NASA's Artemis program is built on the assumption that a lunar crew can count on support from Earth arriving within a reasonable window. Difficult, expensive, but not impossible. Mars is where the picture changes. At its closest approach, the red planet sits about 140 million miles out, nearly 600 times that same driving distance to the moon. Resupply from Earth takes months, not weeks, timed around the narrow windows when the two planets align favorably. Emergency evacuation with anything humanity currently knows how to build is essentially impossible. A Mars crew has to be largely self-sufficient, carrying spares, tools, and enough expertise to solve problems without a house call, trained for years to improvise before they ever leave Earth. At least out there, a conversation with Earth still closes inside an hour. Slow, but not silence. Beyond Mars, repair from Earth does not get harder. It disappears. At Jupiter, a replacement part would take years to arrive, if anyone could even launch one aimed at a moving target billions of miles away, on a trajectory that has to be calculated years in advance for a rendezvous that cannot be corrected once underway. At Saturn, longer still. At the heliopause, the idea stops making sense at all. No resupply ship built by any agency on Earth could reach a craft that far out in any useful stretch of time. The part would arrive decades after the fault that made it necessary. Past that boundary in true interstellar space, repair is not difficult. It is not expensive. It is meaningless. A craft crossing the Oort cloud is alone in the most complete sense that word allows. A failed circuit stays failed. A frozen fuel line stays frozen. A hole torn open by some passing fragment stays open. There is no engineer to consult, no spare part in a warehouse somewhere with its name on it, no shuttle standing by. There is no one to call. There is no one coming. Whatever breaks out there either fixes itself, or it stays broken forever. In 2024, something did break, on the one craft best positioned to show what that actually looks like. Voyager 1's flight data subsystem malfunctioned, and the spacecraft began sending back garbled nonsense instead of the columns of numbers that pass for its science and engineering reports. Characters that should have meant something and did not. For months, engineers at the Jet Propulsion Laboratory worked the problem from more than 15 billion miles away, sorting through data that made no sense, testing theories against a machine they could not see, touch, or visit, until they finally narrowed the fault to a single, failing memory chip, one component out of thousands on a computer built before most of them were born. Their fix was not a repair in any conventional sense. No one touched the spacecraft. No one could. They wrote new code that moved the corrupted function into an unused corner of memory elsewhere on board, tested it as thoroughly as a team on Earth can test anything running on hardware 15 billion miles away, and transmitted it across that same gap. From detection to resolution, the whole process took about 5 months, and Voyager 1, when that fault hit, was still close enough to talk to. Push the same failure out into the Oort cloud, where a single round trip eats months or years instead of hours, and 5 months of diagnosis stretches into years, maybe longer. The fix, if the team ever found one, could arrive long after whatever it was meant to save had already frozen, drifted, or corroded past the point of mattering. Not slow, too late, and already decided before anyone on Earth had finished asking what went wrong. Now put people on that same trajectory. A crew beyond the heliopause carries everything it will ever need. The ship itself, the air inside it, the water, the food, the medicine, the accumulated expertise of everyone who might one day need to improvise a fix. All of it has to be aboard at launch, or built from whatever can be gathered along the way. On Earth, that second option is always there in the background. A hardware store, a hospital, a stranger with the right tool. Out past the heliopause, it quietly stops being an option at all. There is nothing to gather. No asteroids drift between the Oort cloud and the nearest star waiting to be mined. No pockets of water ice sit ready to melt. No ore waits to be refined into a replacement part. The space between the stars is not a resupply depot. It barely qualifies as matter at all. It is not perfectly empty. Out there, a single cubic centimeter holds roughly 1 or 2 atoms of hydrogen. The same cubic centimeter of the air filling your lungs right now holds something closer to 10 quintillion molecules. Empty is the wrong word, only in the strictest technical sense. In every sense that matters for staying alive, it is exactly that empty. Not thin, not scarce, empty in every way that counts, and no amount of searching changes the count. You cannot build a circuit board from 1 atom per cubic centimeter. You cannot drink it. You cannot patch a hull breach with it. So a crewed mission bound for interstellar distances has to be sealed and self-contained for the entire voyage. Decades at the fastest realistic speeds. Centuries more likely. Every tool, every spare part, every gram of medicine, every calorie of food has to be counted, tested, and loaded before the engines ever fire, because nothing more is coming after that. No rescue ship, no emergency landing site, no friendly port to restock at along the way. The margin for error on a voyage that long is not small. It is close to zero. This was the 4th of the 5 collapses, and the one that makes every earlier failure permanent once nothing can be fixed. Everything that breaks simply stays broken. One collapse still waited, quieter than this one but no less physical. The challenge of carrying enough spares to survive a journey that long, and what that spare weight costs a spacecraft that still, first, has to leave the ground. A margin close to zero, the last collapse ended on. The obvious answer to a margin that thin is simple enough. Bring backups. If one computer fails, a second takes over. If one thruster clogs, another fires in its place. If one antenna cracks, a spare unfolds and keeps transmitting exactly where the broken one left off. Engineers call this redundancy, extra systems built in and held in reserve for the moment. Something inevitably breaks. And it is the reason spacecraft survive as long as they do. Power thinning in silence, signals fading past detection, position going stale, repair disappearing entirely past a certain distance. Redundancy is the margin standing between a mission that shrugs off a problem and one that quietly dies from it. But redundancy is never free, and it never has been. Every backup adds weight. Every spare needs its own power supply, its own wiring, its own place to sit inside an already crowded frame. Every extra piece of hardware is one more thing that can eventually fail on its own schedule. One more countdown running alongside everything else's. Take just one example already described. A backup flight computer, identical to the one already running a spacecraft's most essential functions, might sit powered down for years or decades, waiting for a fault it may never see. That second computer still needs its own share of electrical power, its own thermal management, its own bracket bolted into a frame that already has too little room and too little mass to spare. Multiply that same trade-off across every critical system on board. Computers, thrusters, antennas, sensors, and the reserve required to keep a mission safe starts to rival the size of the mission itself. Engineers spend entire careers balancing redundancy against mass, against power, against the small volume left over once every other system has already claimed its share. For a mission measured in years, that balancing act holds. Stretch the mission far enough, and it stops holding. Picture a spacecraft built to operate for 50 years, half a century of continuous work with no dock, no depot, and no supply ship anywhere along the route. It needs 50 years of consumables set aside from the start. 50 years of spare parts for every system that might fail, not once, but potentially several times over. 50 years of fuel reserved for course corrections that cannot be skipped. 50 years of declining power, the same slow radioactive countdown described earlier, factored into every design decision from the very first sketch. Add all of it together and the mass budget is already staggering, and that tally does not yet include a single kilogram of the instruments actually meant to do the mission's work. Mass is the one constraint spaceflight never forgives. Add a kilogram to a spacecraft, and it needs more fuel just to accelerate that kilogram. That fuel carries its own mass, and moving it takes still more fuel again. The relationship does not add. It multiplies, described by what engineers call the rocket equation, weight and fuel locked together in a spiral where the cost of carrying something grows faster than the something itself. This is the tyranny engineers actually mean when they invoke that name. One of the most unforgiving formulas in all of physics. Add one backup part to a spacecraft, and the true cost is never that one part's weight alone. It is that weight, compounded again and again, all the way back to the launch pad. No chemical engine, no ion drive, no propulsion system flying today changes that arithmetic in any meaningful way. How many spares does a machine actually need to survive 5 centuries with no one checking in? Stretch the same 50-year mission out to 500, and the arithmetic does not bend. It breaks. 500 years ago, no telescope had ever been pointed at the sky. Galileo would not build one for nearly a century more. That is the span now being asked of a single sealed machine, launched once, sealed shut, and left entirely alone for the whole of it. The mass budget for a voyage that long is not staggering anymore. It is unachievable. Not with any propulsion system flying today. Not with anything seriously proposed for tomorrow. You cannot carry enough spare parts to maintain a spacecraft across 500 years. You cannot carry enough fuel to keep correcting its course, year after year, across that stretch of time. You cannot carry enough shielding to absorb 5 centuries of the radiation, already drifting in from every direction of the sky. Not underfunded, not underengineered, closed off entirely by the very same equation that lifts every rocket off the ground in the first place. Bring more spares, and the spares themselves become the problem. More weight demanding more fuel demanding more weight again, until the numbers fold in on themselves and no design survives the climb. This was the 5th and final collapse. Power failing in silence, communication failing loudly, navigation failing as an afterimage, repair disappearing past a certain distance. And now the last line of defense against all 4, redundancy itself, gone the same way the rest went, not through any single dramatic failure, but as a limit built directly into the mathematics of leaving. And none of it has said a word yet about what a spacecraft or a crew is actually flying through once it clears the support architecture entirely. A stretch of the solar system so vast it looks like empty space from any distance worth naming, and so quietly crowded, once you look closely enough, that empty turns out to be exactly the wrong word for it. That same darkness is where the 30,000-year crossing already described is waiting, and distance is not the only hazard hidden inside it. That darkness already has a name. The Oort cloud, the same distant shell behind the 30,000-year math from the very start, is not a boundary drawn on a chart. It is a place, and a place, unlike a boundary, has things in it. No telescope has ever seen it directly. What exists instead is a trail of evidence. Comets falling in toward the sun from every direction of the sky, on orbit so long that a single one can take millions of years to complete. Trace those orbits back far enough, and they all point to the same origin. A vast, roughly spherical shell of icy bodies beginning around 2,000 astronomical units, out and reaching 100,000 or more. Nobody has photographed it. Everybody who studies it agrees it is there. Estimate its population, and the number turns uncomfortable fast. Hundreds of billions of objects, quite possibly more than 1 trillion, carrying a combined mass that could add up to several times the mass of Earth. These are not specks of dust drifting through the dark. They are cometary nuclei, the solid cores that grow tails once they fall close enough to the sun to feel its heat, ranging from a few hundred meters across, roughly the length of several football fields, laid end to end, up to tens of kilometers, bodies large enough to pass for a small moon. A full spectrum, pebble to near planet, all of it orbiting in a place with almost no light to see by. Almost no light is the operative phrase. At 2,000 astronomical units, the sun delivers about 4 million times less light than it gives Earth. Push out to 50,000 astronomical units, and the gap widens to 2.5 billion times dimmer. Past moonlight, past starlight, into something closer to no light at all. These bodies do not glow on their own, and they reflect too little of what little reaches them to register on any telescope pointed from Earth, or on any sensor riding along with the spacecraft itself. So a craft moving through that shell at the same 17 kilometers a second that has carried Voyager for nearly 50 years would have no way to see what sat ahead of it. No warning light, no blurred shape drifting into view, no time to steer around anything. Just contact, and at that speed, contact and the end of the mission arrive in the same instant. Here is where the arithmetic should offer some comfort, and for a while it does. The Oort cloud is enormous, and even 1 trillion objects spread across a shell that size occupy an almost vanishing fraction of the total volume. Neighbouring bodies may sit billions of kilometres apart. Run the odds on any single year of the crossing, and a collision is close to negligible, unlikely enough that dismissing it would feel reasonable. But the crossing does not take a single year. It takes 30,000 of them. Stretch a small annual risk across that many years, and the comfort drains out of the number. A 1 in a million chance each year sounds harmless in isolation, and compounded across tens of thousands of years, it becomes a risk worth taking seriously. Run a 1 in 100,000 chance each year the same way, and it works out to something close to 26% across the whole transit. Better than 1 chance in 4. The exact figures shift, depending on assumptions nobody can fully verify, because the cloud itself has never been directly observed. So its density and the true spread of object sizes remain genuinely uncertain. What does not shift is the shape of the problem. A small risk, repeated often enough, stops behaving like a small risk. Not a wall to crash into. A minefield to drift through, blind, for 30,000 years straight. That is the honest description. Sparse but real. A field that never announces where the danger sits. Only that it exists, somewhere in the dark ahead. And it cannot be armoured against. No shield stops a body the size of a house arriving at 17 kilometers a second. This is not the fine haze of interstellar dust that a hull might absorb or deflect. That hazard is still ahead, waiting in the emptiness beyond the cloud. This one is different in kind. Not grit, mass, not erosion, annihilation. The only response left is acceptance, a probability rather than a plan, a slow roll of dice repeated every single year for 30,000 years running. That is what waits inside the darkness the last 5 collapses already described. The Oort cloud is only the first hazard hiding there. Between its scattered objects, filling the emptiness that looks so complete from any distance worth naming, is something else. And it does not wait 30,000 years to start doing harm. It does not wait at all. It is already there, filling every cubic centimeter of the space beyond the heliopause, and it never lets up. Call that space empty and you would not be entirely wrong. A galaxy-wide average of roughly 1 atom per cubic centimeter, thinner still near the sun, is about as close to nothing as matter gets. This stretch of the galaxy already proved itself close to a vacuum earlier in this journey. But near nothing is not nothing, and the mistake is thinking that emptiness means safety. Not matter, radiation. The interstellar medium is defined less by what drifts through it than by what races through it. And what races through it can kill a person, kill a circuit board, and wear down almost anything built to last. These are called cosmic rays, and the name undersells them. They are not light. They are shrapnel, atomic nuclei stripped bare of their electrons and hurled to nearly the speed of light itself. Mostly protons. Some helium, carbon, oxygen, occasionally an iron nucleus riding at 90% of light speed. Ordinary matter, in other words, moving with energy ordinary matter should never carry. The most energetic cosmic ray ever detected packed the kinetic force of a professionally pitched baseball into a single subatomic particle. One proton, thrown like a fastball, with nothing anywhere in its path built to catch it. Most of that violence is inherited. A star 20 times the mass of the Sun exhausts its fuel, collapses, and detonates. And the shock wave from that single death keeps accelerating particles outward for thousands of years afterward, long after the light of the explosion has faded from any sky. Neutron stars colliding and black holes flaring add more of the same, each one another source pumping particles into the same shared bath. None of it is aimed at anyone. It simply fills the galaxy, indifferent and constant. The leftover violence of events that finished burning out long before any of it reaches anything built by human hands. Inside the heliosphere, some of this gets filtered. The Sun's own magnetic field, the shield this piece is already named, bends and scatters a share of the incoming particles before they reach the inner solar system. Not all of it. Cosmic rays still reach Earth, still reach flight crews logging enough high-altitude hours to carry a measurably larger dose than the rest of us. Still reach astronauts on the space station who absorb roughly 10 times the radiation of someone standing on the ground beneath them. For the mid-energy rays that do most of the biological damage, the heliosphere cuts the intensity by somewhere between 30 and 50%, sometimes more depending on how active the Sun happens to be. The highest energy particles barely notice the shield is there. Voyager 1 confirmed the difference the moment it crossed. Its instruments recorded the jump directly. Cosmic ray intensity climbing sharply right at the heliopause, exactly where the models said it would. Beyond that line, the bubble is gone. The deflection is gone. Every particle arrives at full strength, from every direction, without pause. For a machine, this is survivable, at least for a while. A cosmic ray striking a memory chip can flip a bit. A single event upset, corrupting a stored number or occasionally triggering a command nobody sent. Deep space hardware is built with that in mind, radiation-hardened chips, layers of error correction watching the data for exactly this kind of quiet corruption. The Voyagers have absorbed thousands of these hits across nearly 5 decades, and the correcting software has caught nearly all of them, with only a handful serious enough to need help from the ground. But the strikes do not stop, and outside the heliosphere they land more often. More rays mean more upsets, and eventually a higher chance of a multi-bit error. The software cannot untangle on its own. Every upset the software fails to catch chips away at the reliability of a computer built in the 1970s, and every year outside the shield ages that computers' electrical brain a little further. Transistors slowing, memory losing its grip on the charge that holds a number in place, on top of whatever the plutonium clock is already doing to its power. So much for the machine. The body fares worse. Every cell carries a strand of DNA that a single passing cosmic ray can break as it goes through, the way a bullet parts a thread. Most of that kind of damage a cell can repair on its own. The heavy nuclei cannot be repaired the same way. An iron nucleus crossing a cell at 90% of light speed does not snap one strand. It drags a column of destruction the length of the cell, ionizing hundreds of molecules in a line the repair machinery cannot keep up with. The cell dies, which the body absorbs without difficulty in small numbers, or it survives with the damage half repaired and divides again anyway, carrying the error forward. Not a wound, a mutation with a head start. NASA's career radiation limit, revised in 2022, sets the ceiling at 600 millisieverts of cumulative exposure, the same figure applied to every astronaut regardless of age or sex. A 6-month stay on the space station stays comfortably under it. A 3-year round trip to Mars, roughly 18 months of it spent in transit with minimal shielding, can approach that ceiling or cross it depending on the year and the shielding carried along. Beyond the heliopause, the dose does not slow down for the rest of a mission that might run for decades. The obvious answer, wrap the crew in something heavy, turns out to be the wrong one. Lead stops X-rays cleanly. Against a cosmic ray moving at nearly light speed, lead is not a wall. It is a trigger, shattering on impact and spraying a shower of secondary particles into the very cabin it was meant to protect. Adding more lead adds more shrapnel, not less. The materials that actually work are light ones. Hydrogen most of all, its single bare proton too small a target to shatter the way a heavy nucleus does. That is why water and a hydrogen-rich plastic called polyethylene both show up in NASA's shielding studies. Useful, ordinary substances doing a job lead cannot. Even so, cutting the dose in half on a Mars-length mission calls for tens of centimeters of that material wrapped around the crew's living space, adding tens of thousands of kilograms to a spacecraft that already fights for every kilogram it carries. And a mission stretching for decades would need to scale that mass up further still. And even then, the dose never reaches zero. The highest energy cosmic rays, the ones carrying more than a giga-electron-volt of energy in a single nucleus, pass through any shielding a rocket could realistically lift. No thicker wall solves that problem, only a thinner dose. There is a cost beyond cancer, and it is a newer one. For decades, the conversation around cosmic rays stopped at tumors. It should not have. NASA's Space Radiation Laboratory has run these doses through mice, simulating what a deep space crew would absorb over years, and the animals came back changed. Slower to learn, worse at remembering, more anxious, with measurable changes inside the hippocampus and the prefrontal cortex. The brain's memory and decision-making machinery, alongside a chronic, low-grade inflammation that does not resolve, a kind of static that never turns off. The findings are still preliminary. Mice are not people, and nobody has run this experiment on a human crew for the obvious reason that nobody could. But the direction of the evidence is consistent, and on a mission with no relief crew and no evacuation, a slow decline in memory, judgment, and emotional control is not a footnote in a research paper. It is a threat to whether the mission survives at all. Radiation reaches the mind before it ever touches a muscle or a bone. But the mind is not the only thing 30,000 years of drifting was going to wear down. The mind is not the only part of you the void goes to work on. The body carrying it fails too, quietly, on its own separate timeline, driven by nothing more exotic than gravity's absence. Radiation is not the only force turned against a human crew. The body evolved under a narrow set of conditions. Gravity pulling steadily downward, air pressing evenly against every surface, a day and night cycle timed by a spinning planet, an immune system built by constant contact with a living biome and with other people. Every one of those conditions is degraded or gone the moment a mission leaves them behind, and the consequences are not speculation. They are documented, measured, and in some cases, alarming. Start with the skeleton. In microgravity, bone density does not decline gradually the way it does with age. It drops almost immediately. Bone breakdown continues at its normal rate, while the body's ability to build new bones slows to a crawl. And the weight-bearing bones, the spine, the pelvis, the legs, lose density at roughly 1 to 2% a month. Run that forward across a single year, and the loss reaches 10 to 15%. Something like 1 bone in 7, gone inside 12 months. NASA's studies of astronauts on year-long space station missions confirm the damage does not fully reverse. Recovery on Earth, when there is an Earth to recover on, takes months to years, and some of the internal lattice that gives bone its strength may never rebuild completely, no matter how long the rehabilitation runs. Not partial, permanent. No trip home to reset it. For a multi-decade voyage, the loss simply keeps accumulating, year after year, skeleton after skeleton, until an ordinary movement, bending to pick something up, lifting a supply crate, even a hard cough, carries a real risk of fracture. Muscle goes the same direction, faster. The large postural muscles of the legs and back, the ones that fight gravity every waking hour on Earth, begin to waste within days of weightlessness. Fibers shrink, strength falls, and because the heart is a muscle too, it stops pumping against a full gravity gradient and grows weaker along with everything else. Which is why astronauts returning from 6-month missions often cannot stand up without the room spinning, a condition doctors call orthostatic intolerance. Onboard exercise slows all of this. It does not stop it. And the equipment that makes exercise possible needs maintenance, spare parts, and power. 3 things that grow scarcer every year of the trip. The eyes are next, and this one surprised the people who found it. More than half of astronauts on long space station stays develop measurable vision changes, a condition with its own name now, spaceflight-associated neuroocular syndrome. Without gravity pulling blood and spinal fluid downward the way it does on Earth, pressure builds inside the skull, presses on the optic nerve, and reshapes the eyeball itself. In some astronauts, the change never fully resolves. On a mission stretching decades, a crew that depends on sharp vision for repairs, monitoring, and navigation could be looking at that world through eyes slowly losing their shape. The immune system weakens too. Studies show measurable immune dysregulation during spaceflight, including the reactivation of viruses that have been dormant for years, chickenpox's virus, and the one behind mononucleosis among them. In a small, closed population with no fresh contact with the outside world, that means infections spread more easily and the body fights them off less well, exactly when there is no hospital to fall back on. Each of these problems is manageable by itself. A 6-month mission with a working return trip and a full medical team waiting on the ground can absorb bone loss, muscle wasting, blurred vision, a weakened immune system, one at a time. A multi-decade mission cannot, because none of it happens in isolation out there. It compounds. A body already weaker in its bones is more likely to fracture. A body with poorer vision is slower to catch a warning sign. A body fighting a low-grade infection recovers less well from either. Not one failing system, several feeding each other. The body that evolved for Earth begins failing the moment it leaves Earth's conditions, slowly and systematically, and past the heliopause there is no return to reset the clock. The decline simply continues for whatever remains of that person's life. And decline was always survivable when help was close. Every crewed mission in human history has flown within reach of rescue. On the space station, a capsule sits docked and ready. A heart attack or a burst appendix can be sealed inside it and back on Earth within hours. Even Mars stretches the return trip to months, but the option still exists. Earth is still there at the end of it. Beyond the heliosphere, evacuation stops being a fallback and becomes a fiction. Surgery, if it happens at all, happens on board, performed by a crew member with some training, but no real surgical practice, using instruments packed away years or decades earlier that may already have degraded. No specialist is a radio call away. If a medication runs out or expires, nothing replaces it. That last point matters more than it sounds like it should. Most pills stay effective for 2 to 5 years under good storage. None have ever been tested, let alone approved, for the decades a mission like this demands. Push past 10 or 15 years, and many medications lose their potency or break down into something the body should not be given at all. NASA has looked in early studies at manufacturing drugs on board from raw chemical precursors, but the technology barely exists. The range of drugs it can make is narrow, and it needs exactly the power, upkeep, and expertise the mission is already short on. Something as ordinary as a cracked tooth makes the point cleanly. Over any multi-year stretch, a dental abscess or an impacted wisdom tooth is close to inevitable. Routine on Earth, treated in an afternoon. Out there, it can spread into a full-body infection, and in a crew member whose immune system radiation has already worn down, a jaw infection can turn life-threatening. Treating it needs antibiotics that may have expired, sterile surgical drainage, training nobody on board fully has, and follow-up care competing against every other demand on the ship. Not a routine visit. A crisis with a dentist chair nowhere in sight. Multiply that single example across every category. Fractures, more likely with weakened bone. Kidney stones, more common in microgravity as the body's calcium chemistry shifts. Cardiac events, more probable as deconditioning advances year after year. And psychiatric emergencies, depression severe enough to impair judgment, breaks from reality brought on by years of stress and isolation, conflict escalating inside a crew with nowhere to walk away to. Each one draws on supplies and expertise that only shrink with time and never restock. Health, on a mission like this, is not a footnote. It is a central constraint on whether the mission survives at all. A crew that cannot keep itself well cannot keep the spacecraft running, and losing a single member to something treatable back home is not only a tragedy, it is a permanent loss of whoever would have stood the next watch, made the next repair, caught the next warning sign. This is exposure in its most intimate form, not exposure to radiation or cold or vacuum, but exposure to the ordinary fragility every human body carries. The fragility that medicine on Earth spends its whole existence quietly managing. Out there, nothing manages it. The body breaks down the way it always has. The difference is that this time, someone has to watch it happen with only what they brought. The body, though, was never the whole story. Everything around it, outside the whole, was still working against the mission too. Outside the whole, the smallest attacker in the whole story is something you could lose on a fingertip. The interstellar medium carries dust, not the household kind, but grains of silicate, carbon, and ice worn down over billions of years by dying stars, by supernovae, by the slow erosion of larger bodies into smaller ones. Each grain measures a fraction of a micrometer to a few micrometers across, thinner than a strand of hair sliced 1,000 times over. The medium out there is sparse. The grains are real, and the spacecraft is moving through them the entire time. Here's what makes them dangerous. Not size, velocity. A grain under a millionth of a gram sitting still on a table would do nothing to anyone. Put that same grain in the path of something moving at 17 kilometers a second. Voyager's own cruising speed, the one already clocked against the Oort cloud's drifting bodies, and the physics changes completely. Kinetic energy scales with the square of velocity. Double the speed, and the force does not double. It multiplies by 4. Work the scaling forward. At 17 kilometers a second, a grain a tenth of a millimeter across, smaller than a crystal of table salt, carries enough force to excavate a crater many times its own diameter in solid metal. At 1% of light speed, close to 3,000 kilometers a second, that same grain punches through centimeters of hole. At 10% of light speed, the energy released by a single particle reaches the range of a small explosive charge. A grain 1 micrometer wide, at those velocities, strikes with the force of a small bullet. The faster you go, the more lethal the emptiness becomes. For the Voyagers, this is a slow-burning risk, not a sudden one. Some shielding comes built into the structure itself, and the odds of a mission-ending strike in any single year sit low. But low is not zero, and the transit ahead runs 30,000 years. Even a tiny annual probability, compounded across a span that long, edges steadily towards certainty. For a probe built to move faster, the same math turns vicious far sooner. A 20-year mission at 10% of light speed meets a dust environment delivering thousands of times more kinetic energy per unit area than the same 20 years at Voyager's plodding pace. And shielding does not scale the way you would hope. The Whipple shields flying on the International Space Station work by placing a sacrificial bumper ahead of the hull, so an incoming particle shatters against it and spreads its energy as a debris cloud across a wider wall behind, instead of drilling straight through. That trick holds at a few kilometers a second. Past a few hundred, past a few thousand, both the shield and the grain stop behaving like solids at all. Impact energies run high enough that bumper and impactor flash into plasma in the same instant, and that plasma can still tear into whatever sits behind it. High-velocity shielding, at the speeds any real interstellar mission would need, remains an unsolved problem. No design on paper answers it yet, and every impact that does not end the mission still costs something. A pitted antenna, a scarred thermal blanket, a dulled optical coating, each strike shaving away a little more capability than it had the day before. Impact is not the only siege underway. Space carries a reputation for cold, and the reputation is earned. The universe's background temperature, the leftover heat of the Big Bang itself, sits at roughly 2.7 Kelvin, more than 300 degrees colder than the lowest temperature ever recorded on Earth's surface, at a research station buried in Antarctica. Close to the sun, a craft's temperature comes mostly from its orientation. Sunlit side warming, shaded side cooling, held in balance by reflective coatings, insulating blankets, and heaters tuned to keep electronics inside a narrow, comfortable band. Beyond the heliopause, the sun stops contributing almost entirely. What warmth remains comes only from the spacecraft's own power system, and a faint trickle from that background glow left over from the birth of the universe. Let the heaters fail, or let the power feeding them fall too low, and the craft begins sliding toward the ambient temperature of deep space itself. Not a season. A one-way slide toward a temperature with almost nothing left in it. At 2.7 Kelvin, metal that once flexed under stress turns brittle enough to crack. Lubricants freeze solid. Seals shrink and open gaps they were never meant to have. Long before matters reach that extreme, the electronics are already finished. Most spacecraft components are rated to function only down to roughly negative 40 degrees, the one point where the Fahrenheit and Celsius scales finally agree, cold enough that circuits misfire, batteries stop delivering current, and solder joints crack as dissimilar metals contract at different rates. This is the same fight as power, seen from the cold side of it. The Voyagers hold their critical systems warm using waste. Heat bled off their dying generators, and as those generators weaken, the waste heat shrinks with them. Engineers have already switched off heaters on components judged expendable, letting parts drift below the temperatures they were designed to survive. The margin thins every year, and someday a critical part will cross below its working limit for good. There is no way to warm a frozen thruster line or a cracked circuit board from 15 billion miles away. A crude crossing makes the arithmetic worse, not better. A human body needs something close to 60 to 80 degrees to function, so the habitat has to stay heated for the length of the entire voyage. And every watt spent holding that temperature is a watt stolen from communication, from navigation, from life support, from the science the mission was built to gather. Then, there is the hazard that touches no instrument at all. A crew beyond the heliosphere would face an isolation no human being has ever lived through. Astronauts on the space station, a few hundred miles up, still see Earth fill the window, still talk to family with barely a delay, still know a capsule sits docked and ready to bring them home within hours. A crew on the moon is farther out, but Earth stays visible, close enough that the tether never really loosens. A Mars crew is the first to feel something different in kind, Earth reduced to a bright dot, a conversation stripped of its back and forth by the delay, isolation that shows up clearly in ground-based studies built to simulate it. But even at Mars, the crew knows the way home exists. Months of travel, but real. Past the heliosphere, that changes completely. Earth stops being distant and becomes functionally absent, not destroyed, just gone. In every sense a person could feel from that far away. The sun itself stops behaving like a sun. It shrinks to just another star, indistinguishable from thousands of others scattered across the same dark field of view. The constellations that once marked home slowly warping into shapes nobody would recognize. Every visual thread, every familiar voice, every anchor tying a person to their species and their history and their home simply stops reaching that far. Communication, if it survives the distance at all, arrives in days, weeks, sometimes months. So a message home gets its answer long after the moment that prompted it has passed. No real conversation. No comfort in real time. Nothing but the small group already on board, indefinitely. None of this is speculation dressed up as danger. Antarctic winter over cruise, submarine personnel on long deployments, volunteers sealed away for the Mars 500 isolation study, all show elevated depression, sharper conflict, broken sleep, and creeping mental fatigue. And those effects show up even when everyone involved knows the isolation will end and rescue remains possible. Strip out the ending. Strip out the possibility of rescue, and the strain does not level off. It accumulates for as long as the mission lasts. Sailors on the long ocean voyages of the 15th through 18th centuries endured months and years of exactly this kind of hardship. Disease, hunger, isolation, and yet even the worst of those crossings happened on a planet where sailors still saw familiar stars, still breathed open air, still knew land, and other people waited somewhere over the horizon. An interstellar crew keeps none of that. The void it enters is not only physical, it works on the mind the same way radiation works on the body, quietly, cumulatively, and just as capable of killing. Every one of these dangers had, up to this point, been named on its own. Power, signal, direction, repair, radiation, the body, now dust, now cold, now this. None of them out there had ever actually been asked to work alone. Out there, none of them ever really worked alone. Step back far enough and a single shape sits underneath every hazard this hour has named. Engineers study each danger the way engineers study anything. one variable at a time, power on its own chart, radiation on its own chart, communication, dust, cold, isolation, each measured separately. But deep space does not present them one at a time. It presents them together, linked through a chain of dependencies so tight that the failure of one system speeds the failure of every other. That linkage, not any single hazard, is the real danger. A spiral no fix can break, because one condition drives it. Distance. Watch the cascade run. In the planetary years, everything holds within its margins. Sunlight distant but present. A nuclear generator already carrying the real load. Messages hours late but strong. Crossing toward the heliopause, the first system slips. Sunlight drops to nothing useful. The generator becomes the only supply, and it is already fading while the delay crosses the line past which Earth can no longer troubleshoot in real time. Then the heliopause itself and the shield disappears. Cosmic ray intensity steps up to a new baseline, and the slow damage starts. A flipped bit, a degraded transistor. Here is where the compounding turns serious. Weaker power leaves less current for the heaters, forcing choices about which components stay warm. A part left too cold does not die outright. It degrades. A colder battery delivers less current. A colder valve answers more slowly. A colder sensor drifts off calibration. The same hardware keeps showing up in every column. The computer plotting a course as the computer absorbing cosmic ray strikes. The antenna reaching for Earth is the antenna sandblasted by dust. Not a chain where cutting one link stops the rest. A web. Pull one thread and the whole structure shifts. Not the loud kind of failure. The quiet kind, where each small loss makes the next slightly more likely, until 1,000 tiny thefts add up to a machine that can no longer take care of itself. Inside the solar system, this cascade rarely runs unchecked, because a backstop exists. Mission control catches early drift, uploads a patch, swaps to a backup. Beyond the heliosphere, none of that reaches, and the cascade runs faster the farther it goes, because every additional mile weakens an already failing signal and drains an already shrinking power budget. Not a harder version of ordinary spaceflight. A different condition. Inside, the margins narrow, but hold above zero. Beyond, they reach zero and keep falling. Test that against the most serious real proposal for reaching another star. Breakthrough Starshot, announced in 2016 with Breakthrough Initiatives funding, would use a ground laser array to push gram-scale probes to 20% of light speed, fast enough to cross the gap between Earth and the Moon in a few seconds. Reaching Alpha Centauri, roughly 4 1/3 light years out, in about 20 years. Even this runs into the same compounding forces. At that speed, a single grain of dust scattered somewhere within a volume equal to 40 Olympic swimming pools becomes an acute threat, and over 4 light years a probe crosses a column holding thousands of them. A craft this small cannot carry a real transmitter, so its answer home crosses that same distance on a whisper of laser light, faint enough that one clear image could take years to confirm. Proponents call it a research program, not a mission, with a launch window somewhere between the mid-2040s and the 2060s if every open problem gets solved first. Tiny, disposable, barely able to speak, and not guaranteed to survive the trip. Beyond that sits a chasm no engineering closes. A crewed mission needs food, water, air, shielding, power, and medical care sealed aboard for decades or centuries. Hardware holding together over timescales nothing has been tested against. And a crew whose minds survive farther from another human than anyone in history. No credible study concludes that it is achievable with anything close to current technology. Generation ships, sleeper ships, fusion-powered vessels remain sketches, not blueprints. The energy to push a crude habitat to even a modest fraction of light, speed outstrips what human civilization produces, which forces a new condition into the open. Mission autonomy by necessity. Even the Voyagers, at their staggering distance, still take commands and lean on a ground team for the decisions that matter. Their independence is partial. Past a certain distance, that arrangement breaks. The delay too long and the signal too faint for Earth to steer anything in real time. So the craft, or the crew, decides alone. Not by preference, because physics leaves no other option. A Mars rover is autonomous inside a plan a ground team wrote and can still revise. A ship past the edge of the solar system has no ground team at all, only a question sent home that gets its answer years later, if it arrives, long after it stopped mattering. Humans improvise. History is full of survival in conditions that should have ended badly. But every one of those stories happened on a planet with air, water, food, and some sliver of a chance that help was coming. Past the heliosphere, none of that sliver survives. No rescue, not today, not ever. Studies of long isolation find that this knowledge alone, that no evacuation is coming no matter what happens, is its own stressor, showing up as more withdrawal, more fatalism, worse judgment, carried for as long as the mission lasts, which returns this hour to the small spacecraft that started it. Voyager 1 sits roughly 173 astronomical units out, the farthest thing humans have built, due to cross one light day from home in November 2026. Its power keeps fading. Its instruments keep going dark, one at a time. Its voice is a whisper caught only by the largest dishes on Earth, and its computers, pushing 50 years old, have absorbed decades of cosmic ray strikes while running colder than designed, tended by a team that can only speak to it in 2-day round trips. And it has not left the solar system. It crossed the heliopause years ago, but the sun's gravity has not let go, and will not for a very long time. The true edge, where the Oort cloud thins into the space between stars, sits tens of thousands of astronomical units further out, 30,000 years away at Voyager's own cruising speed. It will spend every one of those 30,000 years still inside the system that built it, and long before it reaches that outer edge, it will fall silent. The generators will drop below the threshold for running one instrument. The heaters will fail. The thrusters, out of fuel or frozen solid, will leave the antenna pointed at nothing. Then it drifts. A quiet piece of metal and circuitry carrying a golden record no one will ever play, roughly the weight of a compact car, through a dark so complete the nearest star looks the same as a billion others. It will cross the Oort cloud without knowing it did, leave without ceremony, and continue for millions of years, cooling toward the temperature of the universe itself, not a triumphant crossing of a line, a slow, irreversible thinning, one system after another, until what remains is not a spacecraft, but a monument, built by ambition and undone by physics. Here is the truth every hazard this hour has pointed toward. The danger was never the radiation, or the dust, or the cold, or the isolation. Those are symptoms. Distance is the disease. Distance drains the power with no way to refuel it. Distance breaks the signal as it thins across the square of the range. Distance erases repair, cancels rescue, strips away the shield the sun once provided, and distance turns a solvable mistake into a permanent one. The cruelest part, none of this feels dangerous while it happens. No turbulence, no alarm, no line to cross. The sun dims by a shade you would not notice today. The signal thins by a fraction you would miss tomorrow. Each day looks almost exactly like the one before it, and that is precisely how it gets you. The losses compound in silence, decade after decade, and by the time the total is unmistakable, It is too late to turn around. You cannot retreat faster than you traveled. The trap does not spring. It closes. So the danger was never a thing waiting out there to be encountered. The danger is the out there itself, the widening gap between you and the only star and the only planet that ever kept anything alive. Every mile costs a fraction of a watt, a fraction of a decibel, a fraction of a degree, a fraction of a chance at rescue, and none of it comes back. The solar system was never just planets circling a star. It is a life support system. The sun supplies the energy. The heliosphere supplies the shielding. Earth supplies the voice on the line, the corrected course, the simple fact of somewhere to long for. Leave that architecture, and it does not thin into something smaller. It ends. The emptiness beyond is not indifferent the way a desert or an ocean is indifferent. It is indifferent the way the space between galaxies is indifferent. Completely, structurally, without exception. The farthest thing humans have ever built weighs about as much as a compact car, carries a record of who we were that no one will ever play, and speaks in a signal so faint it would not light a single point on a screen, and it has not even left home. Not a story about triumph. A story about scale, the gap between what the mind can picture and what physics allows, a harbour and the open water beyond it, and what happens to anything that sails far enough to lose the shore behind it. The shore does not follow. The light does not chase. The warmth does not reach. And distance, patient, absolute, older than every star overhead, simply waits. It does not need to do anything else.